So it was a race. I was going to start at 7:02 a.m. my time, which is a half hour your time, or when it hit 200 people, and they happen almost exactly the same time. So I'll start. Welcome everyone to Software Architecture by Example. You may be familiar with me and myself and Mark Richards already. Mark is also a frequent conference presenter, and in fact is doing presentations at this conference as well. But he and I have also written a book called Fundamentals of Software Architecture. And before that book, we actually put together a series of videos about software architecture. But we also realized and started doing an O'Reilly online class a few years ago called Software Architecture by Example, because while some people like learning about topics like software architecture through sort of exposition and deep sort of exploration, other people like viewing things from a show rather than tell standpoint, driven by example rather than by exposition. And so in our way of creating multimodal ways of presenting this material, Mark and I turned the material inside out and created Software Architecture by Example. So over the next 50 minutes, what I'm going to do is take a problem written in business terms and actually do some architecture on it. Now, we can't do a lot of architecture in an hour, but what I aim to do is to show you the basic structural design steps in architecture driven by an example that is based on one of our architecture katas. So here is my agenda. We're going to touch on all of these things along the way here as way of thinking about what it looks like to build architecture by example. I'm not going to spend a lot of time going into the fundamental details of things like architecture styles and patterns. I did a little bit of that earlier today on your time at the beginning of the conference this morning. But even that was a superficial view of that. We have this video on the O'Reilly Learning Platform, or this book, which goes into great detail. In fact, some of the most detail you'll find anywhere about all the details of these architectural styles that I'm only going to touch on today because we're trying to build an architecture in an hour. So the way we're going to do this is use an exercise called an architecture kata. A couple of my colleagues are actually doing a workshop tomorrow on architecture katas, basically walking through a much longer version of doing this kind of exercise. Now, this was an innovation created by well-known software architect named Ted Neward many years ago, this idea of an architecture kata. And it's based on this observation that how do you get better in anything in life? Well, you practice. How often do you get to practice designing new architectures? Almost never. And so how are you supposed to get better at designing new architectures if you never get a chance to practice doing that? And so this gives you practice designing architecture. So Ted created a whole bunch of these katas and put them on a website. Mark and I, with his permission, took those and then enhanced them. They are on, there's a bunch of them on the Fundamentals of Software Architecture website, which I'll show you at the end of the talk today. And so you can do one of these exercises or several of them yourself if you would like. What I'm going to do today is take one of our katas, going, gone, and walk through and actually build an architectural solution for this. And so Going, Gone is an auction company that wants to take their auctions online to a nationwide scale. Customers choose an auction to participate in, wait till it begins, and then bids during the live auction as if they were there in the room. So we're basically trying to replicate the idea of a live auction as much as possible online. All of the katas have the same basic sections and expected number of users. Here we want to scale up to hundreds of participants per auction and then potentially up to thousands of participants because we want to have simultaneous auctions. The requirements, these are all written from a business standpoint, just like you would capture from a business user. Bidders can see a live stream of the auction and see all bids as they occur. Auctions must be as real-time as possible. Yes, possible is doing a lot of work there because we realize that you can't do an actual real-time system online, but as much as possible, we'd like to replicate the idea of an auction. Both online and live bids must be received in the order in which they were placed. So ordering is quite important here, just like in a real auction. Bidders register with a credit card, and the system automatically charges that card if the bidder wins. So we take payments, or probably through a third-party processor, but we still have to process that. And participants must be tracked via a reputation index. What we're looking for here, and this is something you'd have to get clarification for, is we don't want people coming and bidding on things and then never paying, or running up the bids and then disappearing. And so we're looking to avoid basically internet trolls showing up at our auctions. The additional context here, the auction company is expanding aggressively by merging with smaller competitors. All this additional context are things that may not be written down in requirements, but are part of the decision you have to make as an architect. So for example, if the nationwide auction is a success, we want to replicate this model overseas, so we have future growth plans. We're not budget constrained. Some of these katas have budget constraints, which make them more difficult. We're not budget constrained here. And the company just exited a lawsuit where they settled a suit alleging fraud. And so now, let's say that you're an architect and you've been given this problem and asked, okay, we need a software system that implements this. One of the first things you have to do is figure out what kind of architecture characteristics that you want to support. And the first thing you have to realize, and let me talk about these first and we'll get into characteristics, is a few laws from our book. I wanted to bring these up first because these will keep coming up over and over again throughout the course of my talk. The first law of software architecture, which I actually alluded to this morning in my other talk, is that everything in software architecture is a trade-off. And there's a corollary to that law that if you think you found something that isn't a trade-off, it just means you haven't identified what that trade-off is yet. What that suggests is there's no perfect solution to any kind of architectural problem. Everything is in one set of trade-offs or another. And so one of the things that I try to instill in new architects is to get away from terms like best or worst, because it's really, they're not really better or worse, it's just different sets of trade-offs. And so let's talk about architecture characteristics and the first step in designing an architecture like this. So architecture characteristics is mine and Mark's term for all the things outside of the domain. So our domain here is the auction site, going, gone, which I will refer to as GGG interchangeably. So that's our problem domain. So we have to write design software to handle an auction. But we also have to think about a lot of other stuff like scalability and performance, and maybe elasticity and security. All those other things are what we call architecture characteristics. Some people call these non-functional requirements. We don't like that name because non-functional suggests that it's not functional, which is obviously not true. You also hear these called system quality attributes. We also don't like that name because it implies a quality assurance kind of thing after the fact versus something that you have to consider before anything else, which is commonly true here. Permita says CFR, that's the cross-functional requirements. We don't care for that term because it has the word requirement in it, which makes them bleed into the domain level requirements. The informal term for these are illities, whatever you call them. This is at least one half of your design effort is figuring those things out as well as your domain. And it's important to figure those things out because this will drive you toward a particular architecture style. For example, if you analyze your problem and only find one set of architecture characteristics, particularly around operational things like performance, you can safely build a monolithic architecture. But if you have very different kinds of performance needs in different parts of your system, then you need a distributed architecture. So this is fundamental to some of the core decisions you make in architecture. We wanted to identify and define what we meant by these architecture characteristics. So here's our definition. These are things that specify non-domain design consideration, influences some structural aspect of the design, and critical or important to application success. The bottom one there is mostly filtering criteria, because the more of these you support, the more complex your architecture becomes. And so we have a general rule of thumb, Mark and I, of when you go through an initial pass to try to identify these, try to identify a 7 or fewer. Now, why do we say 7, this magic number? Well, and this is really per architectural element, which I'll talk about in a second. There's nothing magical about 7, but the problem is the more of these you support, the more complex your design becomes. And often these things interfere with one another. Architecture characteristics are synergistic, meaning that, for example, if I improve security, I will probably impact performance. And so the more of these you support, the more likely you are to get them all tangled up with each other. And so part of your job is to pick the fewest number of these you can get away with. And so that 7 number is just a way to keep you from going out of control and picking dozens of these and try to force you to prioritize them. So toward that goal, let's actually identify some driving architecture characteristics. We're only going to do going, gone here. When Mark and I do the full-blown 4-hour version of this, on O'Reilly Online, we also do one called, a simpler one called silicon sandwiches. So let's look at our friend going, gone here. So the first thing we will notice here is this is an online auction, and we want these things to be as real time as possible. So that certainly suggests some of these operational kind of architecture characteristics. Availability. Obviously, people needs Sharana SS is completely right there. Terrible with your names, I apologize. Is exactly right there. High availability, because we want people to be able to find the auction, but we also want reliability, which is availability is actually a subset typically of reliability. Reliability means that if I'm participating in an auction, that my connection doesn't disappear all of a sudden. I have to relog back in, which would be annoying. And at least a certain level of performance. We want to try to replicate as live, as real time as possible. So there has to be some level, a good level of performance here to be able to replicate that. We want this to run, so sometimes you get lucky as an architect, and they'll actually tell you in the requirements some of the characteristics they need and use the actual word. We need to operate at a nationwide scale up to hundreds of participants per auction, and if it's successful, we're going to expand overseas. That's obviously scalability. But we don't just need scalability. We also need something else. So scalability is typically the ability to support a large number of concurrent users as people log onto the website with some sort of performance SLA. But if you look at the nature of an auction, what happens toward the end of an auction? People get more and more excited, and more bids come in, and more people show up. And so you also need elasticity. This is the ability to handle bursts of users all at one time. This is a subset of scalability. So some systems can be scalable but not necessarily elastic, but some people need elasticity as well. And so that's exactly what we're seeing here, is we need both scalability and elasticity for this solution. What about this one? Participants must be tracked via a reputation index. Now, the temptation as an architect is to start thinking about all the security implications or the ways to track this. So auditability, for example, might be one of these, or logability. You'll notice how the ility shows up a lot here. That's the ilities, any English word you can take and turn it into an architectural characteristic by adding ility to it. Mark's favorite version of this is, because what you're really trying to prevent here is anti-trollability, which is what Mark really likes. But this is actually a bit of a trick question, because this is not an architecture characteristic at all. Because the question you need to ask yourself as an architect is, do I need special structure in my architecture to support that? So one of the clues that this is not an architecture characteristic is that I had to go find a business person to describe what this means. Because scalability is a well-known concept in architecture. Elasticity, performance are all well-known concepts in architecture. Reputation index is not. So that's the first clue that this is actually part of the problem domain and not an architecture characteristic. Remember, we have to write all the software to manage an auction in addition to these architecture characteristics. And so now the question becomes, do I need special structure to do this reputation index thing? Well, this is going to be some kind of rules engine or some kind of domain specific language. Do I need a special structure to handle that? No, this is just going to be part of the design of my code. And so the point here is that not every requirement will create an architecture characteristic. And so it's your job as an architect to filter through these and figure out which ones do in fact have an impact on the structure and the architecture style you're going to implement this in. So what about this one? Bidders register with a credit card and the system automatically charges the card if the bidder wins. Well, this one is pretty easy. Security. But now the question becomes, is this a primary or secondary concern? Obviously, no architect wants to design an insecure system. But you can also design a system that's so secure that it's almost impossible to use. And so where do you find the happy medium there? Well, this is another one of those cases where I probably don't need special structure to manage security, particularly if I'm not holding on to credit cards, if I'm using a third-party payment processor, and I'm very careful with architectural governance around never keeping credit card numbers in plain text, always using encrypting and salting and hashing and a bunch of other best practices, then I don't need to build a special part of my architecture just to handle credit cards. Now, that last line in the additional context would make me, as an architect, go find somebody with a higher pay level, so an enterprise architect or a CTO or someone, and make sure that they were okay with us not having a special, for example, a special distributed service that only handles payment. That's exactly what I mean, Sharon, in terms of special structure, like having its own distributed service that is more hardened than the others, for example. That's what I mean by having a specific part of my architecture to support that. And so as long as I'm good with architectural governance, I don't need that special structure. Now, what this means is you need to be really good at architectural governance, because you don't want somebody to make a mistake while they are dealing with something critical like security or payment or credit cards. Fortunately, there are really good techniques for both codifying those kind of governance rules and making sure they get executed on a continuous basis. And that is the subject of the workshop that I'm doing tomorrow morning on workshop day, Building Evolutionary Architectures, which is about building automated architectural governance around things like, if I wanted to design my system to handle credit cards, how can I make sure that they handle those things correctly? So that's the topic of my workshop, which is coming up here shortly. So that looks like a pretty good set of architecture characteristics. So that's what we're going to go for on our first pass. Now, one of the things that's worth mentioning here is that architecture is always iterative. This design is always iterative. And so you don't have to get this exactly right the first time through, because the next thing we're going to do is start designing some components. And as we design those components, we'll come back and revisit this list to make sure that it still makes sense. You have to be iterative in architecture design because it's impossible to guess and get it right the first time, virtually impossible. Mark, my writing partner, has a great quote that all architecture becomes iterative. Agile just realizes this and does it sooner than other architectures. And so let's talk about components. So this is the basic flow chart that we're going to walk through in identifying components. The first thing we're going to do is identify some initial components. And this is very much a guessing game because we don't have any part of this system designed yet. And so this is really just designing some empty buckets to put stuff in and see how well things, our requirements map to those components. Then we're going to assign requirements to those components and see how well our component structure matches what we need to design from a domain standpoint. Then we're going to analyze roles and responsibilities. Who's going to interact with this component? What do they need to do with it? What kind of behaviors? Then we're going to analyze architecture characteristics and go back and re-look at those architecture characteristics and see if they have an impact on our component design, and then restructure and go through this feedback loop again. So let's do this and identify initial core components for our system. Now, we have nothing so far. We have a problem domain, which is about auctions. That's all we really have. And so one of the things we're going to have to do is define some components. And one of the easy traps to fall into that you should definitely try to avoid is one that Mark and I refer to as the entity trap. So one of the things you might notice here is that, okay, we have auctions. Well, we could create an auction manager component that creates auctions, browses auctions, and schedules auctions. Oh, there's a typo there. That should be auction, not autumn. Item manager, because we have items that would create items, display items, and upload images. And bid manager, which places bids, display bids, and track bids. Do you notice anything common about these names? Well, they're all just some entity manager. So this is not an architecture, this is an object relational mapping. Don't just take the entities in your system and build components around them. Because what you're going to find is, while that is a way to design things, when you start trying to make these things interact with each other, it's going to be a nightmare. And so this is something you need to try to avoid. If your system is so simple that this design is sufficient, you don't really need an architecture. You need to download a framework like Grails in the Groovy world or Rails in the Ruby world, which are basically tools that allow you to point some code at a database schema and it'll build UIs for you. So that's all you're really doing there. But our auction problem is much more complex than that. And it turns out there are lots of different ways to derive components. And some of this has to do with what sort of software development process you're using. For example, if you're using something like domain-driven design, then you'll probably do an event storming exercise to figure out what are our domains or workflows, and then what kind of messages do they need to pass between one another. And so that workflow or event storming approach would say, okay, let's identify what domains we have. We need to create an auction. Well, to create an auction, what do we need to do? We need to be able to find one. And when we found it, we can sign up for it, we can watch it, and we can place a bid. So this is a common workflow with my ecosystem. And so that would have me create components that look like this: an auction creator component, a browser, a registration, a streamer, and a bid capture component. And that's a perfectly good way to delineate this problem space. And this would be very common if you're using domain-driven design or workflows. We're going to do something slightly different here, but basically based on the same concept of this event storming kind of approach, but it flips the roles around to an actor action versus purely on the actions. So event storming primarily focuses on the workflows and actions. Here we're going to add the actors or the people interacting with the system, and you'll see why this is an appealing approach to this problem in just a second. So let's look at actors and actions, and here we have three primary actors. We have bidders who view a live video stream, place a live, view it, both the video stream and the bid stream, and then place bids. We have the auctioneer who enters live bids into the system, probably through a proxy, some sort of secretary or scribe as part of the auction, receives bids online, and marks items as sold, also interacts with the live audience there. And the system is the thing that is the glue that does all the work, starts an auction. When the auction's finished, after the item is sold, it makes a payment, and it's the thing that tracks bidder activity. One of the reasons we're taking this specific approach for this problem is highlighted right here. Because one of the things I'm going to have to do in this system is think about architecture characteristics. One of the first things you have to figure out about your system is, does it have, so let's talk for a second about operational architecture characteristics. Things like performance, scalability, and elasticity. So just those architecture characteristics for a moment. One of the first questions you have to ask yourself is, do I have one set of operational architecture characteristics or greater than one set of architecture characteristics? Because that's going to lead me to either a monolithic architecture style or a distributed architecture style. Because if I have one set of architecture characteristics, I can safely build a monolith, which is much simpler, much easier to deal with. If I have multiple sets of operational architecture characteristics, I need to choose a distributed architecture. And this slide right here tells us all we need to know. Because think for a minute about bidders. We have hundreds or thousands of bidders. And so for bidders, we need scalability, we need elasticity above all, and performance. But what about the auctioneer? Per auction, we have one auctioneer. We don't need scalability for the auctioneer at all. Let's think about reliability for a second. Now, clearly it's bad if one of my bidders tries to make a bid and they've lost their connection to the auction and have to relog back in. That's annoying for my bidder. But if my auctioneer loses connection to the auction, the entire auction is done. And so reliability for the auctioneer has got to be sky high. So just looking at this delineation of responsibilities tells us this is going to be a distributed architecture. I need more than one set of architecture characteristics. Therefore, I need a distributed architecture like microservices or an event-driven architecture, because I need to be able to support these different levels of architectural operational behavior. So let's take our actors and the things they need to do and build some components from them. We don't have any yet because we're starting from scratch. And so this is really an exercise about empty buckets. So first thing we're going to do is start an auction. That's the first thing you do for an auction. So what do we need? Well, we need a component to do that. We have none. So let's go ahead and create an auction session component to manage our auction stuff for us. The next thing we need to do is track bidder activity. So now the question is, should auction session do that or should it be its own component? Well, I don't want that to be part of auction session, and so I'm going to create a bid tracker component. But obviously, if I'm going to track bids, it has to have awareness of what's happening with the auction, and so there needs to be connectivity between these two components. So that's exactly what I'm doing here, is identifying what components I'm going to need and what sort of interaction they might have with each other. And you can see here, this is what will lead me to restructure some of them. If I end up creating two components that have a lot of interaction, then I probably just need a single component. So now I have a bid tracker, so that looks pretty promising. Now, one of the things that's a requirement is to view a live video stream. So do I need a new component or should I use an existing one? Well, this doesn't sound like the job of either auction session or bid tracker, so it sounds like a new component to me, a video streamer component. And that, when you think about architecturally, has its own set of interesting problems, which is a read-only stream as real-time as possible. Same for the live bid stream. That's also its own little unique set of problems. But is that something that we can get from an existing component? Nope. So we need a bid streamer as well. So you can see how this is kind of working here. I try to identify if existing components will work, and if not, I will pick a new one. So the next thing I might need to do is place a bid. Anything that I have so far handle that? Not really. So I need a bid capture. But if I capture a bid, I need to put that in the bid tracker. And I need to stream it back to the other bidders because we've got other bidders who may be involved in this auction. Okay, so what about receive an online bid? Should that be a new component or should it be one that I've already got? Well, I've already got bid capture. That's exactly what bid capture is for. And so that seems like a reasonable place to receive an online bid, the same place we place a bid from one of the bidders. So that makes perfectly good sense. What about enter live bids into the system? New component or existing one? Well, that's really just bid capture. Well, that's exactly what that's doing, and so we can use that to both enter live bids and receive new ones. What about mark item as sold? Is that a new one or an old one, an existing one? Well, that's really the job of auction session. Remember, that was part of its job early on, was the system, which was to mark things as sold so that we can do things like payment. So what about make a payment? Do I have a component for that, or is that one for an existing one? Nope, I'm going to need another one for that for payment, and that, of course, is going to be referenced from my friend auction session. Receive online bid. Shouldn't this point to a bid streamer? Receive an online bid. Well, it goes into bid capture, and then bid capture goes into bid streamer. So the streamer is what streams it back to all the other bidders. We need to, for both the all the bids that come from other bidders and from the live auction, to get back to the bidders, and so that's why it goes through bid capture, and then from bid capture back into bid streamer. So that looks like a reasonable set of components here, because we've looked at our problem domain and analyzed how the domain fits together. But wait a minute. Remember this flow chart that we were talking about? Now we need to analyze architecture characteristics on the components that we have now. And now we see a problem. Remember, let's go back to the original diagram here. Remember what we figured out about the operational difference between auctioneers and bidders. Auctioneers need high levels of reliability and availability, but don't need high scalability. Bidders need super scalability and performance at the expense, perhaps, of availability or reliability. So I cannot have a single bid capture component for both of them. Even though from a domain standpoint, that's what it's doing, is capturing bids. But when I analyze the architecture characteristics, I need another component. I need both bid capture and auctioneer capture. There are two separate components here that from a domain standpoint seem to do the same thing, but from an architectural characteristic standpoint need to do different things. They need to support different levels of performance, scalability, and elasticity. This is the reason that you go back and revisit those architecture characteristics and iterate on this design to make sure that you're building something that fits not only the domain that you're working on, but also all these other architecture characteristics that you need to be able to support for this problem space. Now I have a reasonable set of components, and so now I will translate those into actual components. Let me go back one for just a second. You'll notice that for this exercise, Mark and I used sticky notes or virtual sticky notes, and that's very much on purpose here for something that I referred to in a blog post I did several years ago as irrational artifact attachment. If it takes you 2 days to build a really beautiful diagram and somebody suggests that it's wrong, you'll push back against that because you know how much effort it took to build that beautiful diagram. That's what I call irrational artifact attachment. If it's something on a whiteboard or a sticky note, you'll tear that thing up without thinking twice and build a new one. And so in the early stages of architecture, don't create really pretty, elaborate kinds of diagrams. Do it as lo-fi as possible, and then once you've iterated on it, you can create something that's a little more pretty. And so now we can take the components that we identified and just make them components and start thinking about how they need to interact with each other. Auctioneers interact with auction session and auctioneer capture, and of course that needs to go to bid streamer. So that it needs to get those bids back to my bidders. Bid capture goes to auctioneer, and that's of course what captures from the bidder. Bid streamer and video streamer goes back to the bidder as well. And so now I've started stitching together how I think these components are going to communicate with each other. Okay, so now we need to decide what kind of architecture style to implement these components in. I know that I'm going to need a distributed architecture, so I cannot choose a layered architecture or microkernel or something like a modular monolith, so it has to be a distributed architecture. And I'm not going to go through all these architecture styles because we don't have time for that, and I did that earlier this morning. So what I'm going to do instead is look at some candidates and then figure out if I want to use those or not. So the four candidates I want to look at here, and I'll describe these briefly. A service-based architecture. This is one where I have, this is not as restrictive as a microservice. I have a single relational database, bigger domain classes than in a microservice, and typically a single user interface. A space-based architecture I'll talk about specifically in a second. A microservice architecture is the one that is the current trend in architecture right now, with really super high degrees of isolation at the domain level. And one of the nice features of microservices for us is that each service can have its own set of architecture characteristics. Basically, architecture characteristics are scoped at the service level in microservices, whereas it's at the system level with something like service-based architectures. And then events are appealing because while it's a very low-level plumbing kind of architecture, it also allows you to have very, very high degrees of performance and scalability, which is appealing for us. But it's very complex to build all that stuff from scratch. Particularly transactional behavior is really tough there. Space-based architecture is a special case. Elasticity is one of the things that we really, really need here. And space-based architecture is hyper-optimized for elasticity. And it's this fairly complex architecture with a high number of moving parts that does basically hundreds or thousands of processing units and then feeds all that down via eventual consistency to a relational database. But really, really high champion in terms of elasticity. And if you rate these in terms of our problem space, where 3 thumbs is good or bad, and green is good and red is bad, if you look at a service-based architecture, it's not overwhelming in any of these. It's not particularly great at elasticity. The biggest thing against service-based architecture, though, is it's really primarily supports one set of architecture characteristics because of that database. I can't really have very different levels of scale if I only have one database, because it's all going to be contingent on that database. So we can knock that one off probably. Option 2 is space-based, which is hyper-specialized for elasticity, but tough for transactional behavior, and we have transactions here, and very complex, a lot of moving parts. And then option 3 is maybe I don't need to pick one of these. Maybe I should choose a hybrid, because microservices give me really great scalability, but not great performance. That is typically the Achilles heel for microservices is performance. But event-driven architecture has really good performance. And so you can't really do architecture math by saying, well, if you combine the two, we'll get the best of both worlds. But one really common way to improve the performance in microservices is to use events and asynchronous messages. And so that seems like a pretty appealing option for us. So that's how we're going to design Gone. We're going to use a microservices architecture, but use events to pave over some of the more critical performance parts of my architecture. So here's my component diagram that I generated before. By building microservices, the next step I need to decide here is, okay, I have my components as designed as workflows, and that matches with the microservices very nicely. The next question then becomes, Shiranya asked about reliability. That is a concern in microservices, but you can make that better by using a service mesh and redundancy and service naming, and have redundant services running. So that is solvable in this architecture. The next thing we need to decide from these components is, where should data live within this architecture? Because not all of these are going to have data. It's really only the ones that need something to persist. And so now I can translate those to services and start thinking first about, okay, where should persistence live? within this architecture. Auction session doesn't actually need any persistence because it's really just live. It does need, bid tracker does need persistence. And so the next thing I need to figure out is, okay, once I have persistence, how should these communicate with each other? The first step in architecture is synchronous versus asynchronous. The next step is implementation detail. And too often architects get into the implementation detail right away. The fundamental architectural concern here is synchronous versus asynchronous, because those follow on to a whole bunch of other architecture implications. One of the things that I'm recommending architects do, in fact, is when you do drawings in something like Visio or OmniGraffle, draw the core topology, which is just boxes and lines first, with dotted lines for asynchronous and solid lines for synchronous, and then build another layer to layer on top of whatever your implementation is going to be, whether it's REST or AMQP or some detail like that. So given that that is our architecture, we can now translate that into services. And we have here what is the first pass between our architecture. So you can see here in my auction session, it's using asynchronous messaging to handle things, to send things over to, for example, bid tracker and auto payment. My auctioneer capture, notice I have auctioneer capture and bid capture. Both of those have levels of scalability. That's what the stack of boxes mean there. But obviously I need a lot more for the bidders than for the auctioneer. This has an API layer. This allows me to use the things like the BFF pattern, the backend for front end pattern, to give a specialized user interface to some people like the bidders versus the auctioneer. Notice that one of the things that we document in an architecture like this is what kind of messaging we're using, and some overlay here. Permita is asking, why is bid capture asynchronous? Well, one of the reasons that you make something like that asynchronous is that both auctioneer capture and bid capture need to feed things into bid tracker. And let's say that I have 1,000 concurrent users for bid tracker and I have auctioneer capture with one person. If those are synchronous, the auctioneer is never going to get in. If I use asynchronous queues, I can use patterns like the ambulance pattern or do some other load balancing across those to make sure that bid tracker gets all of those in the best order that I can get. I don't want a lot of synchronous calls between parts of my architecture that have very different operational architecture characteristics. Auctioneer capture and bid capture have very different levels of scale, and so I don't want either of those relying on each other, and so using asynchronous message queues allows you to balance some of that difference between those architecture characteristics. And one of the things that we typically do in an architecture like this is document some of the decisions we've made about these things. So for example, using asynchronous pub sub between bidding services, the common format for this is the architecture decision record. And this is a good example of one of those. Bid capture needs to move forwards to the bid streamer. This can be done using asynchronous P2P or pub sub messaging or REST via the online auction API. The decision here, so we put out the context and the options, and we put the decision here. We use asynchronous messaging between bid capture, bid streamer, and bid tracker. Bid capture doesn't need any information with bid streamer or bid tracker, so we can make that asynchronous and not have to rely on that. This is actually pretty close to the question that Permita was asking. But one of the things that goes with every one of these decisions and architecture decision records are the consequences. These ADRs are created both for your own future self, because you're going to come back to this decision in 6 months, but other people, so that you understand what forces were in play when you made this decision. Bappy is asking which component needs the highest reliability. I would say probably the auction session or auctioneer capture would need equally high levels of reliability, because if either one of those die during the course of the auction, nothing's going to happen. Of course, bid tracker needs reliability as well. But you can see I actually have different levels of reliability across these different services. And that's the most important observation here, is that this is definitely a distributed architecture, because I do need different levels of reliability and scalability between these different components. All right, so I'm just about out of time. So to summarize, I mentioned this before, there are no right or wrong answers in architecture. Rather, it's always about trade-offs. I showed you a solution for going, gone. Is that the correct solution? I don't know. It's a solution. But there are lots of different ways you could solve this problem and probably build a better solution than the one that we created here. Don't get caught up on this idea that there's one perfect architecture and you're trying to solve this equation. There are lots and lots of different ways to solve problems. Your job as an architect is not to find silver bullets, but rather analyze trade-offs and try to come up with the best collection of trade-offs you can.